In this video, we will be looking at quadratic inequalities. We're going to start by solving quadratic inequalities by looking at a graph. It says, based on the graph, find the set of all x values for which the points P of x comma y are on the graph and y is greater than 0. Enter your answer using interval notation. So this uses a lot of words to try to convey something very simple. We are finding the x values such that y is greater than 0. So we want all the places on this graph that have an we're finding all the x values that have a positive y value. Well, if we have a positive y value, that means we are above the x-axis. That's going to be this section and this section. We're going to assume they go on forever. So the y is positive from negative infinity until we reach 3. And then also from 6 to infinity. We are looking for the places where y is greater than 0. At 3, y is equal to 0. We don't want that, so I want to use parentheses. If it were greater than or equal to, I'd use a square bracket. Same deal with the 6. At x equals 6, the y value is equal to 0, which we don't want, so I'm going to use parentheses. And then to put these two intervals together, I'll use a union. For the rest of this section, we are going to be looking at quadratic inequalities in an algebraic sense. So for solving nonlinear inequalities, we're going to start by moving all the terms to one side. We're going to factor if at all possible. We're going to make the inequality an equation and solve so that we can find the intervals or the boundary points for the solution sets. So we're going to be finding the values that make each factor equal to 0. We're going to put those on a number line. We're going to check the signs for a test value in each interval. We're going to check if it's positive or negative to determine if that interval satisfies the inequality. And then we're just going to write the intervals that satisfy the inequality in interval notation. There are quite a few steps, but after you've done a few of them, things start to click. So we're going to start by solving the inequality x squared plus 7x plus 6 is greater than 0. Our first step in solving quadratic inequalities is always going to be to get 0 on one side. Conveniently, we already have that in this problem. So we have x squared plus 7x plus 6 is greater than 0. So I'm going to factor the left-hand side. That's going to be my first step once I have 0. So this is going to factor into x plus 6 and x plus 1, and we want that to be greater than 0. Now we're going to go into pretend land, and we are going to pretend this is an equation, meaning we have an equal sign. So we have x plus 6 times x plus 1 is equal to 0, and we're going to solve that. If x plus 6 is equal to 0, then we get x equals negative 6. If x plus 1 equals 0, we get x equals a negative 1. We are going to take those values that we just found and place them on a number line. So we have negative 6 and negative 1. I now need to use a test value in each of these sections. So something less than negative 6, I could use, say, negative 7, because negative 7 would be over here. Something between negative 6 and negative 1, I'm going to use negative 2. And then something greater than negative 1, I'll use 0. I'm going to plug in each of these test values into the inequality. And I just want to know whether this expression turns out positive or negative. We already know it turns out 0 if we use negative 6 or negative 1. So each of these values should be either positive or negative. So I'll start by plugging in negative 7. So we have negative 7 squared plus 7 times negative 7 plus 6 is 6, which is positive. So I'm going to put a plus sign here. Plugging in negative 2, I'll have negative 2 squared plus 7 times negative 2 plus 6 is equal to negative 4, so this section is negative. And then if I plug in 0, I'm just going to get a positive 6, so that'll be positive. Now looking at the inequality, I am looking for when this expression is greater than 0. So I want the positive sections. That means I want this section here and this section here. Do I want to include negative 6 and negative 1? Based on the inequality, I don't want the ones that are equal to 0. So I want open circles on my negative 6 and my negative 1. So my solution will be negative infinity until negative 6 parentheses union parentheses negative 1 to positive infinity. We're going to try another one. 3x times x minus 1 is less than or equal to 10 minus 2x. First thing we want to do is get all the terms on one side, so we have 0 on the other side. So I'm going to distribute my 3x through. So we'll have a 3x squared minus 3x is less than or equal to 10 minus 2x. Then I can subtract my 10 and add my 2x. So minus 10 plus 2x, that'll give me a 3x squared minus x minus 10 is less than or equal to 0. Once we have the inequality with 0 on one side, we go to pretend world and we make it an equation. 3x squared minus x minus 10 is equal to 0. And we want to solve this. We could try factoring it. We could try to use the quadratic formula. It's completely up to you. I'm a fan of factoring, so I'm going to try to factor it and see what happens. So we have 3x squared minus x minus 10 is equal to 0. My a value times my c value is a negative 30. The pair that I want that multiplies to give me a negative 30 but adds to give me a negative 1 is a negative 6 and a positive 5. So I'm going to split my negative x into a negative 6x and a positive 5x. Bring down my 3x squared, bring down my negative 10 and my equal 0. I'm going to break it up into the two groups. From the first group, I can factor out a 3x, which leaves me with x minus 2. From the second group, I can factor out a positive 5, which leaves me with x minus 2. So we have the x minus 2 in common, leaving me with a 3x plus 5. If x minus 2 equals 0, then we get x equals 2. If 3x plus 5 equals 0, then 3x equals a negative 5, and x is equal to a negative 5/3. So the two x values that will make this equal to 0 are x equals 2 and x equals a negative 5/3. Once I have those values, I can go ahead and put them on my number line. So negative 5/3 and a positive 2. I need a test value in each region. So something smaller than a negative 5/3 could be negative 2. Something between negative 5/3 and positive 2, I'll use 0. And something greater than 2, I'll use 3. I need to plug them into the expression that has 0 on the other side. I just want to see if it's positive or negative. So 3 times negative 2 squared minus negative 2 minus 10 is equal to 4, which is positive. If I plug in 0, I'll get a negative 10, which is negative. If I plug in positive 3, I'll have 3 times 3 squared minus 3 minus 10 is a positive 14. this time I'm for the sections that are less than or equal to 0. So less than would be negative. So I want the stuff between -5/3 and +2. But I can be equal to 0, so I want closed circles on these endpoints. So the interval I'm looking for is square bracket -5/3 to +2 square bracket. Any number between and including -5/3 and 2 will make this inequality true. Just a couple more to go. We're going to look at 2x squared plus 4 is greater than 8x. So first of all, I need to get 0 on one side, so I'm going to subtract the 8x over. So I'll have a 2x squared minus 8x plus 4 is greater than 0. I'm going to pretend it's an equation now, and I'll have 2x squared minus 8x plus 4 is equal to 0. I'm going to go ahead and try to factor it. I see a greatest common factor of 2 that I can factor out. If I factor out a 2, I have x squared minus 4x plus 2 is equal to 0. My a times c is 2, and there are not two numbers that I can multiply to get 2 and add to get a -4. Since that's the case, I'm going to have to use the quadratic formula. So if we're using x squared minus 4x plus 2 equals 0, we'll have x is equal to -4 plus or minus the square root of -4 squared minus 4 times 1 times 2 all over 2 times 1. So a -4 turns +4 plus or minus the square root of -4 squared minus 4 times 1 times 2 is 8. So we have the square root of 8 all over 2. 8 breaks down into 2 times 4. 4 breaks down into 2 times 2. So that means our square root of 8, we have a pair of 2s, so a 2 can come out. 1 left over, 2 will stay under the radical. So we can write the square root of 8 as 2 times the square root of 2. So we're looking at x is equal to 4 plus or minus 2 times the square root of 2 all over 2, which I'm pretty sure I can simplify, so I'll break up my terms. So x is equal to 4 over 2 plus or minus 2 times the square root over 2, which does simplify into 2 plus or minus the square root of 2. So the two x values we're working with this time are x equals 2 plus the square root of 2 and x equals 2 minus the square root of 2. So I'm going to place those on my number line. Two minus the square root of 2 is going to be the smaller one because I'm subtracting. And that means 2 plus the square root of 2 is going to go over here. But to find my test values, I'm going to have to know about what values those are. So 2 minus the square root of 2 is about 0.59, and 2 plus the square root of 2 is about 3.41. I'm only using that to get my test values. So something smaller than 0.59, I'm going to use 0. Something between 0.59 and 3.41, I'll use 1. And something greater than 3.41, I'll use 4. I try to use small numbers or nice numbers whenever possible because that's what makes me happy. If I plug in 0, I'm going to get a +4. If I plug 1, I'll have 2 minus 8, which is a -6. -6 plus 4 is a -2, so that's negative. And if I plug in 4, I get a +4, which is positive. You may be asking yourself at this point, is it always going to be plus minus plus? Technically, no. But you can kind of logic your way through this. We have a parabola here, 2x squared is 2x plus 4, and that is an upward opening parabola. When we find the x values that make this 0, what we're finding are the places where we cross the x-axis. Since it opens up, our y values are going to go positive, negative, positive. So if that helps you, go ahead and use it. If not, there's an explanation of why we keep getting plus minus plus. In this case, the values that are greater than 0. So that's going to be these ones down here. We don't want equal 0, so we'll have an open circle, and then open circle to the right. So our values that we want are negative infinity until 2 minus the square root of 2, parentheses, union 2 plus the square root of 2 to infinity. Just two more we're going to look at, and these last two are kind of weird. We want to solve the quadratic inequality. We have a negative v squared is less than or equal to negative 3v plus 7. I really prefer to have my squared terms positive, so I'm going to add v squared to the right-hand side. That'll leave me with 0 is less than or equal to v squared minus 3v plus 7. But I also prefer for this expression to be on the left. What I'm trying to make happen is to have this expression greater than or equal to 0. So when I flip it so that my v squared minus 3v plus 7 is on the left-hand side, I need to make sure it's greater than or equal to 0. Because this first expression is saying 0 is less than or equal to, meaning this expression is bigger. That's what this is saying too. All right, if I did a times c, that's 1 times 7, that's not going to factor. So we're going to have to quadratic formula this thing. So we will have v is equal to negative 3 plus or minus the square root of negative 3 squared minus 4 times 1 times 7 all over 2 times 1, which is positive 3 plus or minus the square root of negative 3 squared minus 4 times 1 times 7 is a negative 19 over 2. I need the square root of a negative number. From what we learned earlier, the square root of a negative number is a complex number, but we've been plotting what we solve for a variable on a number line, and that number line only has real values. They're complex, so they don't have a spot on my number line. What this means graphically is that v squared minus 3v plus 7 never crosses the x-axis. So I don't have any place to put on my number line. I don't have any values of v that will make this equal to 0. So I only need one value, and it can be anything I want it to be. I'm going to use 0 because that's my favorite to plug in. If I plug in 0, I get 7, which is positive. Well, I'm looking for the values that make this expression greater than or equal to 0. Every single one of them does. My answer is negative infinity to positive infinity. Remember how I said that graphically this entire graph is above the x-axis, doesn't touch the x-axis? It doesn't touch the x-axis and it opens up. So if it doesn't touch the x-axis and it opens up, that means it has to be above the x-axis. What we're trying to do is find the x values such that the y value is positive. It's always above the x-axis, the y value is always positive. That's why we're getting all real numbers. kind of interesting there. For our last one, we're looking at a negative j squared plus 6j is greater than 10. Like I said before, I like my squared terms being positive, so I'm going to move everything to the right. So 0 is equal to a positive j squared minus 6j plus 10. That is a greater than sign. But again, I really like my squared terms, or my expressions, to be on the left just because it makes me happy. I want my expression to be smaller than 0 this time. So I have j squared minus 6j plus 10 is less than 0. Going into pretend world, I make that an equal sign. I just need to solve it. That one's not going to factor either, so jumping to our quadratic flaw, well, if j is equal to a negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 10, all over 2 times 1, that is a positive 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 10, the square root of negative 4. The same thing is happening as last time. I'm getting a complex number, and I can't plot complex numbers on my real number line. So I'm going to have a number line that looks a lot like the last one. I have a number line. Since no real values will make that 0, I don't have to plot any, I just need a test value. And I'm going to test 0. If I plug in 0, I'm going to get a positive 10. But this time, I want the values that make this expression less than 0, negative. They're all positive. I'm never going to come up with a value of j that will make that negative. So the solution does not exist. There is no value of j that will ever make that negative. In this case, what happens is we are opening up and we're not touching the x-axis. Since we're opening up and we're not touching the x-axis, everything's above, but we want y values that are negative, and that just doesn't happen. So graphically, that's what's going on here. I hope these last two examples opened your mind a little bit. I hope you enjoyed the quadratic inequalities. I think they're a fun section to look at.